Welcome back to Chem 4300. In this video, we're going to finish up Chapter 7 on the electrostatic interactions of atoms and molecules. Now, in the first video, covering the first part of the chapter, we saw how the electrostatic scalar potential generated by, say, molecule 1 here, can be expressed in terms of its electric multipole moment. So it's an electric monopole moment, its total charge, its electric dipole moment, its electric quadrupole moment, and so on. So any point outside this molecule 1, we can calculate its electrostatic potential generated by that molecule and its electric field vector generated by this molecule based on its electric multipole moments. So we came up with this expression here. We came up with a series expansion where the electrostatic scalar potential has a leading term, which comes from the electric monopole moment, the total charge of the molecule. And then the next term is the electric dipole moment vector for the molecule, and then involving electric quadrupole moment, with all of these guys of diminishing importance as we go up in the series here. And of course, from this electrostatic scalar potential, we can calculate the electric field at any point outside the molecule from the negative gradient of that quantity. Now, we also learned that the potential energy for a molecule, say molecule 2, in an electric field can be expressed also in terms of its electric multipole moments. So this molecule could be an electric field due to a nearby molecule 1, which was generated using this expression, or it could be in an electric field, an external electric field, whether the molecule is sitting between two charged capacitor plates, or whether it's the electric field generated by light shining on the molecule. Either way, the potential energy of this molecule can be written in terms of a series expansion in terms of its electric multiple moments, so the monopole moment times the electrostatic scalar potential evaluated at the molecule, its electric dipole moment vector, dot product with the electric field at the molecule, and then the tensor product of the electric quadrupole moment of this molecule times the electric field gradient at the molecule, and so on. So with these expressions, what we're going to do is we're going to look at the force between two molecules. So what we're focused on for the rest of the chapter is the intermolecular forces that have their origins in these sort of electromagnetic phenomena. So what we're going to do is we're going to imagine we take this expression here for the electrostatic field generated by molecule 1 and substitute it into this expression for the potential energy of molecule 2, remembering that we can substitute this guy in here, evaluate it at this point, and then calculate its electric field and evaluate that at that point and substitute it in there, and then similarly for its electric field gradient and so on. And when you do that, and we're not going to do that calculation in this class, but you can imagine it, and what we're going to do is, if you did that, is you would see that there's going to be products of the multipole moments of these two molecules involved in the final expression for the potential energy and the force between them. So you would see that there's going to be a term that's going to, a leading term that's going to be the product of the monopole moment, so the total charge of molecule 1 and the total charge of molecule 2, and that will be the strongest term in the interaction. So if these guys are ions, cations or anions or either one, then that will be a very strong term in this expression for the potential energy. The next term that's going to be there is going to be terms like the monopole moment multiplied times the dipole moment vector. So we'll see that cross term. We'll also see the dipole moment vector of the other molecule, so this guy, with this guy's total charge. So there'll be a cross term of monopole moments with dipole moments. And then we'll see that there'll be dipole-dipole terms, so this dipole moment will interact with this dipole moment, and so on. So for the rest of the chapter, we're just going to focus on the leading terms, so the terms involving the monopoles and the dipoles, and we're not going to look at any more with the electric quadrupole moments. But that's the general idea. Now, in the treatment so far, we haven't really considered the additional electron-electron repulsions that would cause molecules to be repulsive at very short distances. So you can imagine if we had a cation and an anion so far in our treatment, those guys would be attracted to each other and they wouldn't stop. They would just merge together at the origin where they'd be infinitely negative potential. But we know that that's not true. We know that even when a cation and an anion are attracted to each other, at some point the electron repulsions between the orbiting electrons on the cation and on the anion become strong enough to keep them from moving any further close to each other. So we're going to have to add those ad hoc into the treatment, or we're going to be working at very far distances where we don't have to worry about them. But that's something we have to keep in mind. Now, we're going to assume then that all of the forces that we're dealing with can be described as conservative forces, and so they can be described by some potential energy surface, and that potential energy surface will have some minimum where there's sort of an equilibrium distance. There's a balance between attractive and repulsive forces, and taking the derivative of this will give us the force that's being applied, so that the minimum of the potential energy is where the force is 0. Okay, so just a reminder from what we know from the first chapter. Okay, so let's start then by looking at the leading term in that expression. So what we're going to look at is the interactions between ions. So both the molecules or atoms that we're looking at have some non-zero total charge, and there's a potential energy term that looks like this. Now, let's consider the case of, say, sodium and chlorine. So in the case of sodium and chlorine, this is what we would have: the charge on sodium, the charge on chlorine, and then divided by 4 pi epsilon r. That would be the potential energy expression for those two ions. Now, as I said before, that can't be the whole story, because we know that the sodium and chlorine would come crashing into each other at r equals 0, because that's when this whole thing goes to negative infinity. Okay, remember, one of these guys this one has an opposite sign, so that's negative, that's positive, so the whole thing goes to negative infinity. And so we know that that's not going to be the case, so we need some kind of repulsive term to sort of correct this situation. So we're just going to put a little ad hoc additional repulsive term that will overwhelm this at really short distances here. So the form that we're going to take, and there are different ones you can use, we're going to use this form here, where it's just some constant divided by r to the n, where n is some fudge factor that will work out. That's called the Born exponent. That will introduce a repulsive term so that these cations and anions don't collide to each other, but they're actually pushed away to some equilibrium distance. And so we're going to have to figure out where that equilibrium distance is. And so what we'll see here is that if we add that extra term to our expression, to add our ad hoc repulsive term, we know that when they're at an equilibrium distance, that the force should be equal to 0. So if we take the negative derivative of this guy with respect to position, we set that equal to 0, we get an equation which we can solve for that unknown coefficient b. So if I solve for b, this is what I get here. Now if I take this expression, I plug it back into there, then I can simplify that whole thing back to a nice simpler form where it looks a lot like our original expression, except now we have add this extra term, which is 1 over n. So you can see the reason for wanting a repulsive potential looks like this, because you get this nice form where you get this extra term that's 1 over n that gives you the repulsion that you need at very short distances. And this is the potential only evaluated at the equilibrium position here. So this is the full potential. We know the value of b, but we're going to say that if we're at the equilibrium distance where the force is equal to 0, then that's the potential at that point. Now that value of n, which I said is sort of a fudge factor, is called a Born exponent, depends upon the size of the ion that you're dealing with. So different ions will have different values of n that work. So when you have mixed cases like sodium and chloride, generally you use some value that's approximately near the average of the two. So sodium and chloride is 7 and 9, so somewhere around 8 we're going to use for that case. But if you have other cases, you can just calculate some average and you can use that for getting that potential energy minimum. Now, with that expression, we can sort of check to see if we're on track with all of this. We can calculate the lattice energy of a sodium chloride crystal. So say 1 mole of sodium chloride, we can calculate that. And we'll start by looking at, say, sodium. Okay, so what we're going to do is we're going to look at the interactions of the sodium. And we know that each sodium in a sodium chloride structure, it's a cubic structure. And so each sodium is surrounded by 6 chlorines. So if the sodium here, there's chlorine, chlorine up, back, down, in front, back. So each one of those guys is at the equilibrium distance. And so if I take 6 chlorines interacting with that sodium, then I'm going to add this guy up 6 times, and this is what I would get. So it's going to be minus 6 times the fundamental charge unit divided by these constants times 1 minus 1 over n. And that gives you the potential energy associated at the equilibrium distances of 1 sodium surrounded by 6 chlorines. Now, of course, the crystal lattice goes on beyond that first coordination sphere, so we need to continue to add. Now, once you go from the first sodium, you go past the first coordination sphere, the next coordination sphere is going to be filled with other sodiums. So that's going to be a repulsive term. And in that second coordination sphere, which sit at approximately, or so they sit at exactly square root of 2 times the equilibrium distance, then we're going to have 12 sodiums. So if we add up those interactions, we end up with this term added on from the next coordination sphere, which is 12 times the fundamental charge squared divided by this constant, and then square root of 2e here, and then this 1 minus 1 over n. And if we continue this approach, go to the third coordination sphere, we find now there's chlorines. That's an attractive set of terms that we have to add. Then beyond that, a next sphere is sodiums. It becomes repulsive. And then more chlorines, it becomes attractive. And then even more sodiums, and so on, all the way out. So starting from 1 sodium and just doing first, second, third, fourth, fifth, continuing out coordination spheres, you get a expansion. You get essentially a series of terms that you add up. And this sum is such that these values all are getting progressively smaller, but eventually this converges to a number. So numerically, this sum for the crystal lattice of sodium chloride converges to a value of 1.7476. This is something that's called the Madelung constant for sodium chloride structure, something you might remember from when you took general chemistry. So this is the potential energy that the sodium has in this crystal structure. And this Madelung constant, which I said was this value here, is specific to the sodium chloride structure. Other structures, like it's a face-centered cubic, if you have body-centered cubic or simple cubic structures, you can see that there are other Madelung constants that you can look up. But generally, that's just a function of the crystal structure, and that's it. So now we have the expression for, say, 1 mole of sodiums. So we multiply times Avogadro's number. We have the potential energy for 1 mole of sodiums with this Madelung constant there, and then the rest of the expression here. And we can do the same thing for chlorine. If I just redid that a whole argument for chlorine, I get this expression here for the potential energy associated with all those chlorines. The chlorine attracted to the first shell of sodiums, and repulsed from the next shell of chlorines, then attracted to the next shell of sodiums, and so on. That gives me this expression here for the anion. And then when I take them together for the cations and the anions, I add them up, and that's the total energy. Now I have to divide by 2 to avoid double counting, so we'll do that to sort of correct this. But then added together, then we get the total energy of the cations and anions in this lattice. So that's, with Avogadro's number here, makes this 1 mole of the formula unit NaCl. So now we get to the problem that we wanted to do, which was to calculate the lattice energy. So we're going to use a value of 8.4 for the Born exponent. And for the equilibrium distance, we know the radii of sodium cations are 1.02, that chlorines are 1.81. So the sum of those two guys coming together is 2.83. So we'll use that as the equilibrium distance. We have the Madelung constant, we have the equilibrium distance, we have our Bohr exponent here, and you see that we calculate a total energy of minus 756 kilojoules per mole. That's the lattice energy associated with bringing these ions from infinitely far away together into 1 mole of sodium chloride lattice, crystal lattice. Okay, and the lattice energy you can work out from Hess's law, and using the Born-Haber cycle. If you remember this from general chemistry, you would get a value of about minus 787 kilojoules per mole, which is pretty good compared to what we predict based on our simple picture of just monopole-monopole interactions there. All right, so that's just to sort of give you a nice example of that one monopole-monopole interactions. So now let's look at other types of interactions that we can describe using our sort of picture that we've derived so far. So now we're going to look at, say, a ion interacting with a neutral molecule, but now this neutral molecule has an electric dipole moment. So what kind of force are we going to have between these guys? And we can work that out now based on what we've done so far, and you can see that that potential energy function will look like this. So we have a monopole charge at some distance r from a dipole. Now, since we're talking about a dipole, which is a vector quantity, it can have an orientation relative to the internuclear vector connecting the two, or intermolecular vector connecting the two molecules. And this is what the expression works out to be. And I'm not going to expect you to derive it, but if you worked it out, this is what you would find. And so you see there's the orientation dependence, and there's also a 1 over r squared dependence. Something else that I added in here, since we'll probably be considering this type of interaction as the kind of thing you would see, say, in a solvent. So if you're looking at some ion interacting with a dipole moment in a solvent, then you need to correct this by adding in the permittivity of the medium. If this was in the gas phase, then this K would be equal to 1. But in some solvent, looking at these guys interacting, you'd have to include this K to get the right potential. But you can see how this guy sort of depends now on angle and on orientation. It falls off as 1 over r squared in terms of its dependence. And remember, the force is going to be the gradient of this, so that's going to make it 1 over r to the third for the force. Now, in a fluid phase, I've already started mentioning that we're going to put this in a fluid where we have some permeability that we have to worry about. That what we're going to do is that we're going to consider that in a fluid phase, this molecule that has this dipole moment is going to be tumbling. And it's going to be tumbling over all orientations, so that you might imagine, on average, sometimes it's going to be attractive and sometimes it's going to be repulsive, right? If I go back to the previous slide, you see that when theta, cos theta, is equal to 0, when this guy, the angle is 0, then cos theta is equal to 1, and that becomes an attractive interaction. And when theta becomes 180 degrees, this becomes -1, and that becomes a repulsive interaction. So you can imagine that when you're averaging over all values of theta, then you're going to be going +1 down to -1, back to +1 over all possible values. This guy you would think would average completely to 0. But actually, in fact, that the energy of interaction means that when it's an attractive energy, it's going to be a lower value of energy, and when it's a repulsive energy, it's going to be higher. And in this thermal average, what we'll find is that it's going to spend a little bit more time at the lower energy state when it's in the attractive orientation than at the higher energy state when it's in the repulsive form. Now, we need to do a proper statistical mechanics treatment to see why that average is not 0, but we'll do that maybe in next semester if you take 4310. But in this class, we're not going to consider statistical mechanics, so I'm just going to give you the result of that, which is that the mean potential energy expression for this when you have thermal average in a fluid looks like this. So effectively what we're doing is we get the potential energy expression from the previous slide here, and it essentially gets squared, and then it gets multiplied by 1 over kBT, where this is T is the temperature here. So let me just point this out here. So first of all, we see that the thermal average is always attractive. It's always going to be attractive. This is squared, that's squared. So these guys are always positive quantities. Then we have a negative sign here. This will always be attractive. You can see that it falls off as 1 over r to the 4th versus the previous case. The static case was 1 over r to the r squared, right, on the previous slide. Whoop. Here it was 1 over r squared, but now in the thermal average, it's 1 over r to the 4th. And you can see that it decreases in magnitude with increasing temperature. So your expectation that it would average to 0 is correct in the limit that you go to infinitely high temperatures. So very high temperatures, this is 1 over T. That makes this whole thing go to 0, which is what you would expect. But as you lower the temperature, then from the statistical averaging, we find that it spends more time in the attractive orientation and less time in the repulsive term orientation, and that's why we get this net that's potential energy that's not 0. Okay, so let's move on. Let's look at an interaction between dipoles on two different molecules. So let's say we're looking at two molecules that are neutral. They're not ions, but they have permanent electric dipole moments here and here. There's going to be some attraction and repulsions between them. So we're going to look at our expression from the equations. You could derive this. You can see that between two electric dipole moments, the potential energy term would look like this. And again, I'm considering this possibly being in some solvent, so I'm including the kappa term there. And so now we see that there's a dependence. So you can see that, I'll go back to this slide here, but you can see that there'll be orientations where it's always going to be attractive. So this guy is going to be attractive here and here, here and there. Or there'll be orientations where it's repulsive and then things in between, right? So we saw then that this is what the orientation dependence looks like. It's going to depend on theta, this angle, and then also it can reorient around the internuclear vector, or intermolecular vector, I should say, and then there'll be a dependence there, here, and the difference. So if I go to the thermal average, and again, they're going to each randomly reorient, but some of the attractive orientations are going to spend, it's going to spend more time in its attractive orientations than the repulsive higher energy orientations. So the statistical mechanical treatment will show you that you get an average potential energy with this in the fluid phase, with the average thermal average that is going to be given by this expression, where here now we have the dipole moments squared. So the magnitude of the dipole moment squared. Here we have all these constants down here. And now we have a 1 over r to the 6th dependence. And there's, again, this 1 over temperature dependence here. So this 1 over r to the 6th is compared to what it was in the unthermal average case here. It's 1 over r to the 3rd. So this is the thermal average case. It's going to have 1 over r to the 6th compared to 1 over r to the 3rd. So it's going to be a pretty weak interaction between dipoles in the fluid phase. But it is attractive. It's always attractive here. You can see the negative sign here. These are always going to be positive because they're squared. And so it also decreases with increasing temperature. Also, just as you would expect, if you go to infinitely high temperature, this has to go to 0 eventually. All right. Okay, let's keep moving on. Let's look at induced dipole interactions. So now we're going to consider two cases. So one case is we have some ion that has a electric monopole moment interacting with some neutral molecule that has no monopole moment, that has no electric dipole moment. Okay, so this guy it might have a quadrupole moment. We're not going to consider that, but it has no monopole, no dipole moment. And then we're going to consider the case where the molecule over here has no monopole moment, but it has a permanent electric dipole moment, and it's interacting again with our nonpolar neutral molecule. So we'll start with case 1. So this is the case we're looking at. A monopole, an ion interacting with a neutral nonpolar molecule. So what we know is that if our molecule has no ions around it, then it's perfectly neutral. It has no electric dipole moment. But when you bring an ion in, as this ion comes in near this molecule, then it's going to induce a dipole. The electrons are going to be repulsed by this negative charge in this example here, and they're going to move over to this side, leaving this side more positive compared to that side. And now we're going to have a dipole moment vector, which is pointing along the direction, the intermolecular axis here. So this is what we get. Now, if you start out from infinitely far away, then you're going to have you're going to have 0 dipole, but as you start coming in, this induced dipole is going to grow and become stronger and stronger as it gets closer. Now, we learned earlier that the induced dipole moment vector is going to be equal to the polarizability tensor for this species with the electric field that's generating this induced dipole. And that electric field is being generated by this simple charge, this monopole over here, this ion. Now, so if I go back to our expression for the potential energy of this guy in the field of some monopole, so what we have to do is we have to integrate the induced dipole from 0 up to the electric field that we're at. So this guy starts from infinitely far away, where the electric field is 0. And as we bring this charge closer and closer to this guy, then this guy, induced dipole, is going to get larger and larger. So we're going to integrate to get the potential energy of this guy from 0 up to the point where we reach the charge to where we want it to be next to this molecule. So this induced dipole we see is just given by this alpha dot E, and then we're integrating it. For the E, though, we know the exact form for the electric field generated by this monopole, which is given by that expression there. And that's along, this is a vector along the intermolecular axis. So if I put that into my expression there and I integrate it up, then I'll get this expression for the potential energy of this ion-induced dipole interaction. So I'm going to actually rewrite, this is, here you see the isotropic polarizability. So this, we're considering only the case here where we're in a solvent. So we're not going to consider the case where we're in a fixed static orientation. So we're going to assume that we're in a solvent and we're only dealing with an isotropic polarizability. And so in that case, we're going to get this expression here. And you see that we get an expression that depends on the charge squared. It depends on these constants down here squared, and it depends on r to the fourth, inverse r to the fourth. I'm going to replace this guy with the A naught, alpha naught term, which is the polarizability volume, which is a little bit easier to work with, and we'll have this expression for this interaction. So one of the things that you need to keep in mind is that actually there's no need for a thermal average, because the induced dipole is always along the vector that is between the ion and the neutral molecule here. So no matter how it rotates, that induced dipole is always along the same direction. It's along that vector connecting the two. So this value is the average, the thermal averaged value. I mean, you don't need to do a thermal average value. This is the value you'll have in solution, because this dipole is always induced. And so this is the expression we'll use. And this polarizability then is the thing you need to look at if you want to know how strong this effect is going to be. So you can see that for small molecules, it's pretty small, but if you get to bigger molecules, like something with a lot of electrons like CCl4, you get a pretty sizable polarizability here. So you can induce a pretty large dipole in a molecule like CCl4, which is actually neutral. Okay. Okay. So let's move on to dipole-induced dipole interactions. And now we're going to look at a molecule that has no charge but has an electric dipole moment interacting with a molecule that's neutral and has no electric dipole moment. So a nonpolar neutral molecule. So in this case, kind of like the last one, we have an electric dipole moment vector so that is approaching this molecule. And if the negative end approaches it, well, then this molecule is going to have an induced dipole where the electrons are going to move over here and create less negative over here, more negative over here, creating a dipole moment vector that's pointing along the intermolecular bond, vector there, right? And if you work this out, then if you change the orientation of this guy the other way, then this will flip to the other direction, but it still will have the same sort of pointing along the direction of the intermolecular axis there. So for this case, you can work out that you get this expression for the potential energy. So again, it depends on the polarizability of this guy, and then the dipole moment of the molecule that's inducing the dipole over here. And then we have this orientation dependence. So clearly, if this guy changes its angle, then there's going to change the dipole moment that's being induced over here. So there's going to be a theta dependence here. But what you see is that if it still always induces it relative to the orientation of this guy. So what happens is that even if you're doing an averaging over all possible orientations of the dipole, it still comes out to a non-zero value, and it doesn't depend on temperature, because the dipole's always, in these induced dipole cases, it's always induced in a direction that's determined by where the ion or dipole that's doing the inducing is. So it then really will always be pointing along a direction that makes it non-zero on the average. So this gives us this value for the potential energy function. And again, this case now it's 1 over r to the 6. So just to compare for this case with the ion induced, it was 1 over r to the 4th. And for the dipole induced, it's 1 over r to the 6th. Okay, so we're almost done with this tour. The last thing I want to talk about is what are called induced dipole interaction. So imagine now we have two molecules that are neutral and nonpolar, and there still will be an attraction between them. And this brings us to something that's called London or dispersion forces. Let's take probably the most difficult case here. So let's take the case of two helium atoms. Both are neutral, both are nonpolar, and we know that these atoms will eventually condense in the gas phase into a liquid, but that temperature is about 4 Kelvin. So there is an attractive force between heliums, even though they're neutral and nonpolar, but it does require pretty low temperatures to bring them in the gas phase down to the liquid phase. So it's a weak interaction, but it's there nonetheless. Now, to understand this is a little bit more than what we have in this chapter, requires more than what we have in this chapter, because it really involves us looking into the structure of the atom. And so we haven't really treated this in this chapter, but I just want to show you how it sort of comes about. So the general idea is that inside the atom, there's a positively charged nucleus, and there's electrons that are orbiting around in both cases. At any instant, there is some kind of dipole moment vector between the nucleus and the electrons. And so what happens is that these dipole moment vectors between the positively charged nucleus and the electrons on this atom influence the electric dipole moments on this atom, and these two motions of these electric dipoles become correlated in such a way that it leads to a net attractive interaction. So again, I'm not going to get into the details of how this is derived, but it turns out that you need to look at the ionization of these electrons, so how tightly bound those electrons are, and then we also have to look at the polarizabilities of the atoms, and you get an expression like this, where it depends upon the ionization energies and the polarizabilities of the two atoms, and it goes as 1 over r to the 6th. So clearly the more polarizable, so helium is the worst case as you get to, for example, in the noble gases, if you go to neon, argon, krypton, they have greater polarizability, and you would expect them to have higher boiling points because this interaction will get stronger. All right, so that's it for the chapter 7 and all of the electrostatic interactions of atoms and molecules.